Hello, everybody. Thank you very much for watching my talk. I'm going to talk about robust neural network enhanced estimation of local primordial non-Gaussianity with halos and galaxies. My name is Moritz Münchmeyer. I'm an assistant professor of physics at UW-Madison. This is work that's done in collaboration. Well, first of all, primarily done by my graduate student, Yuri Kwasiuk, who is a grad student at UW. This is also in collaboration with Kendrick Smith at Pyramid Institute and with Utkarsh Giri, who was a postdoc at UW and is now a postdoc at Caltech. So the background to this paper is will be based on two papers we published over the last 2 years with some of these co-authors, and most of the talk will be new material that will be published soon. Okay, let's start with a little introduction. I think most people probably will know about local non-Gaussianities and scale-dependent bias. So local non-Gaussianity, right, this parameter f and l constrained to be less than about 5 from the Planck satellite. Local non-Gaussianity is in particular measuring particularly sensitive to multi-field inflation, so light degrees of freedom. And to measure F and L with galaxy surveys, so to go beyond the limits set by Planck, the most promising method to do so is this method called scale-dependent bias of the halo or galaxy field. So scale-dependent bias is one of the famous results of cosmology of the last 20 years. So if here you have the halo or galaxy power spectrum, here you have the matter power spectrum, and if you turn on F and L, you get this kink here on large scales. Mathematically, this bias relation can be written here with the Gaussian linear bias plus this 1 over k square bias that's sensitive to F and L. And the amplitude of this is called the non-Gaussian bias. So different fields can be differently sensitive to F and L. And this method is so popular because it's very robust to nonlinear physics. The nonlinear small-scale astrophysics cannot induce such a kink on the large-scale power spectrum. That's a consequence of Einstein's equivalence principle. And in our work, we try to use a neural network to make this method more powerful, but while keeping its robustness. So without losing the property that's robust to nonlinear physics. And I'm going to explain how that works. So to understand our method, first, I want to remind you how a local non-Gaussianity works. The local non-Gaussianity is a large-scale modulation of small-scale powers. So in a normal Gaussian field, if you have here some large mode, and here you have some small modes, they will be on average having the same amplitude independent of where they lie in the large modes. On the other hand, if F and L is positive, then regions where the large mode is large will preferentially have more small-scale power, as you can see here from this relation. While vice versa, where the large-scale mode is small, you will have less small-scale power. And the reason why scale-dependent halo bias works so well is because halo counting is very sensitive to local primordial power. So it's very sensitive to here the locally measured sigma-8 amplitude. And intuitively, if we can have a neural network that can measure the local primordial powers, the local sigma-8 better than halo density can, then we will get better signal to noise. And in addition, we also want to measure the large-scale mode here as well as we can, also using a neural network that basically amounts to a lowering shot noise. Okay, so we have developed something which we call the pi field formalism. So a pi field is any field that is sensitive to local sigma-8. For example, the halo density, as we've seen, the locally measured position-dependent halo power spectrum. Utkarsh Giri will talk about this at this conference too, or a neural network trained to measure sigma-8. And for all these fields, we can always define a Gaussian bias and a non-Gaussian bias by the relation with the matter field. The non-Gaussian bias here is the reaction of the field to sigma-8. So prior to this work, already 2 years ago, we used this method on the matter field. So we used Quixote and Quixote PNG simulations. We had a neural network that processes the local matter density here and measures local sigma 8. And as you can see on the right, this new neural network field will have scale-dependent bias depending on FNL, as we predicted, has a flat noise as we predicted, and it's very powerful at measuring FNL. However, here the neural network got to see the matter distribution, which of course isn't observable. And so in this new work, we are applying the method to a high-resolution halo catalog from Abacus Summit. And I'm also going to show you some more theoretical analysis of our methods. All right, let's start with this. So I want to motivate that or show that the loss functions we are using to train the neural networks are optimal to constrain FNL. And to do so, we're going to briefly look at some analytic results. So I'm first going to consider the case where we know the matter field and we have n pi fields. So for example, n bind halo fields, or different galaxy populations. And the reason why I keep the matter field here is that it simplifies the algebra and the expressions, but we will later show the results also without the matter field. Okay, so we assume that these fields here have this relation here, so the usual scale-dependent bias power spectra on large scales. And then with some linear algebra, one can show that the Fisher information simplifies to this expression here. So the Fisher information depends only on the non-Gaussian biases and on the noise covariance matrix, but does not depend on the Gaussian biases. This is true for the case where the matter field is known. And so this relation is useful because it motivates a further step, which I'm going to show now. So this motivates that we can define a new single pi field. So based on all, say, our halo fields, we can make a new single field that is this linear combination of the original pi fields. And this new linear combination, the single field pi prime, has the same Fisher information as the original fields. So it leads this form here, invariant. And the Fisher information of this new field will scale as the square root of its noise divided by its non-Gaussian bias. So we see that one pi field, if chosen optimally, is enough to have the full Fisher information. There's no advantage in adding more of them. Now, so we can also show now, along these lines based on this result, that there's an equivalence between measuring FNLs for scale-dependent bias and measuring sigma 8. So recall that a field that has a non-Gaussian bias automatically can be used to measure sigma 8 because of this definition of non-Gaussian bias. And so we can make a statistic that we want to use to measure sigma 8, not FNL, by averaging over the pi field in the simulation. So this would be, for example, averaging the halo count. And then the statistical error on this field here will go as the noise of the field, the square root of the noise of the field, divided by the non-Gaussian bias. And this is the same result we just found in the last slide for FNL. And therefore, like the error on FNL and the error on sigma 8 scales exactly the same. And so in that sense, it's equivalent. Measuring them is equivalent. In particular, that means that a field that's maximally good at measuring sigma 8 will also be maximally good at measuring FNL through scale-dependent bias. And so that means if we want to train a neural network to measure FNL, we don't need simulations with FNL. We can just use simulations that have different sigma 8s in them, and then train the network to learn sigma 8. An optimal loss function to measure sigma 8 is just an MSE loss here, averaged over the simulation. And therefore, since this will give us optimal sigma 8 constraints, this will also give us optimal FNL constraints. We have a bit of a more formal proof of this statement also in the paper. Okay, so in the previous analysis, I said we kept the matter field known, but this is not what's really happening in reality. So now we wanted to know what happens if we have only the pi field. So for example, the different halo mass bins. So in that case, we can also show that it's possible to compress the Fisher information and keep this, the fields and keep the same Fisher information. If we make two fields, one of them is the reconstructed matter field. Here I'm writing this as pi m with Gaussian bias 1 and non-Gaussian bias of 0, and the reconstructed sigma 8 field, which is basically the field we saw just before. And so we derived the optimal weights for these pi fields that are used to define these two new fields and show that these two together have contain the same Fisher information. And now that's very interesting. So we've learned, sort of formally shown something we already expected, which is that to get an optimal measurement of FNL, we want to know two things. We want to know the large scale mode, so the large scale matter field, and we want to know the local sigma 8. And so we add a second loss function here to what we had before. The second loss function here is to reconstruct the matter field given the pi fields. So this basically amounts to trying to lower shot noise by applying a neural network to the halo distribution. And then when we have these two fields, then we should be able to get an optimal FNL constraint based on those. So this is our work now that we're applying to that we're going to apply to the simulations. We're going to use these two loss functions and estimate FNL with that. Okay, so currently we are doing this on Abacus Summit and its extension AbacusPNG with a CNN. Okay, so Abacus Summit and AbacusPNG are very high resolution simulations. So you can see here the mass cutoff, and so they go up to about 10 to the 11 solar masses in halo mass. So they're very high resolution. And here you can, this here is an MC that we run on these simulations with bint with mass bint scale dependent halo bias. So this area doesn't yet have any neural network in it. And you can see that we, for example, here at the lowest bin, we reached the so-called sample variance limit, a cancellation limit, where first the Fisher information sort of plateaus and then goes down again. This is known from the halo model, and here in the simulation, so you can also see that. Okay, so now we want to train these neural networks. So we're going to train a CNN on Abacus Summit, or two CNNs, to learn both the matter field and the sigma 8 field. We do this with Abacus Summit simulations with different sigma 8 values in them. And we let the CNN observe the local halo population statistics. So we let it observe in cubes of 15 megaparsec cubed what is the distribution of mass and concentration. So the halo mass function and the concentration in these cubes. So here you can see this on that plot here, what this looks like averaged over the simulation. And then we find, so now we train it to estimate sigma 8 as we want to, since we know from sigma 8 we can then get FNL. And here you can see that the concentrations help a lot with constraining sigma 8, and therefore will also help a lot with constraining FNL. And here you can see we get very tight error bars on sigma 8 in both cases, actually, since there are a lot of halos in Abacus. Okay, so now we've trained these fields. So this is the result on test data after training. And now we want to use these fields and make an FNL measurement. So we have these two fields now. We apply these now to AbacusPNG, so simulations that have actual FNL in them. Then we run the same kind of MC analyses that we used for pure scale-dependent halo bias. And then we run full MC, as you can see here. And here you can see our results. So these are the error bars we get on FNL. So pi field with concentration, you see we get very tight error bars here. So 30 is the right answer. It's also unbiased. And with only the masses, we get these error bars here roughly. So these ones are comparable with what one would get from the old method without a neural network in the same setting where the matter field isn't known. And you can see that, so for example, the concentrations help by a factor of 4 and lead to very strong constraints. Of course, concentrations are not directly observable, but we'll leave this for future work. Okay, so this was with CNN, and so in my last few minutes, I want to show what we are currently working on. So our method, we showed this new method. We showed that it works with the CNN, but we want to use, rather than using like local population statistics, we actually want to use individual halos and the individual properties, so individual masses, individual concentrations, individual positions, and these should contain extra information. So this can be done with a graph neural network. Several recent papers have shown that graph neural networks are very good at this task. And so we've currently trained our graph neural network on the camel simulations, so not yet on Abacus. But as we've seen, so if we can tighten sigma-8 measurements on camels, we should also be getting smaller FNL error bars due to the theorem we talked about before. And so indeed, we tried on camels. Here, so the MLP, this is comparable to the CNN. So here, this is the error bar we get on in camels give on sigma-8 if we give the model, the neural network, the local halo mass function. And this one is if we give it individual halo masses and positions, and here as a function of cutoff. And as you can see, at the higher mass cutoff, there's almost no extra information in the halo positions. That's because you have a high shot noise, then you have few halos, and so there's not much information. But if you go to lower ones, then the GNN can be better than the MLP by a factor of 2 or so. And as we know, better sigma-8 by a factor of 2 will lead to better FNL by also a factor of 2, assuming the same simulation characteristics. So we are currently working on doing this in Abacus and also on making better experimental forecasts for actual experiments. So we will replace the CNN with this GNN. So in conclusion, we have developed a new formalism to probe squeezed limit non-Gaussianity optimally using machine-learned fields. Any set of observed fields can be compressed to 2 fields which contain the same Fisher information on FNL. For an optimal probe of FNL, we need to optimally reconstruct the local average matter density and the locally observed sigma-8. This can be done with a CNN or GNN, and the sensitivity of the neural network analysis on Abacus is encouraging. We are working on more realistic forecasts for upcoming experiments. Thank you very much for listening to my talk.